Welcome, guys. So last time we saw a simple sampling estimation or one sample estimation using the classical method, article 9.1 to 9.5, and 9.6 was nothing but simply the prediction interval, and that's what we went over. And finally, the tolerance limit, that is 9.7, but that's extremely easy. One can refer this one by their own, by his own. So let me just go through, and then after we solve some examples also. And today we're going to see the two samples, the difference between two means. So two samples estimating the difference between two means. If we have two populations with means nu1 and nu2, because now you have suppose two companies and the production. So one company production rate, that is, suppose you have 100 items and the mean is given by nu1, and suppose second company B is producing also 100 items with mean, or suppose 110 items, n1 and n2 could be different too, and means is different than first one, right? And you have equal standard deviation or different standard deviation for both of the companies. So whenever you are comparing like this, then which production is better, or suppose with the given data, we have the 95% of the confidence interval or whatever we want to find, just like our single sample estimation, same way we can do over here for the multiple, I would say two sample distribution in particular. So if we have two populations with mean nu1 and nu2 and the variance sigma1 square and sigma2 square respectively, a point estimator of the difference between nu1 and nu2 is given by the statistics x1 bar and x2 bar, or x1 cap and x2 cap. And therefore, to obtain a point estimation of nu1 and nu2, we shall select two independent random samples. Make sure that both the selection of the random samples are independent. One from each population, that is size n1, and second one, that is of course size n2. As I told you, they could not be same. It could be same, could not be. Most of the times they are not same. Okay, and we compute x1 bar and x2 bar sample mean for 1 and 2, right? The difference of the sample means x1 bar minus x2 bar, and we consider the sampling distribution x1 cap minus x2 cap. So here we have, you can see here that this, of course, it is approximately normally distributed, and this nu is given by nu x1 bar minus nu x2 bar. There is always nu1 minus nu2, and sigma x1 bar minus x2 bar. Now your n1 and n2 are different, so here it is given in the form of sigma 1 square by n1 and sigma 2 square by n2, because now it depends that sigma 1 and sigma 2, if they are same, you can write simply sigma or sigma square and sigma square. You can pull the sigma square out and you get square root of 1 over n1 plus 1 over n2. But if sigma 1 and sigma 2, they are not same in that case, because in that case you have to rely on this form. Okay, so my z-score will be x bar minus, it is x minus nu over sigma divided by square root of n, right? But sigma divided by square root of n, but here it is, you can see over here it is sigma, because we have sigma 1 and sigma 2, they are different, and that's why you have to have this one under the square root sign, that sigma 1 square by n1 and sigma 2 square by n2, right? So that's and then after we're going to plug the same value over here, just like the previous case. So that's what we are going to see. Let me start with this one, and then after we will be ended up with this formulation. And with the help of this one, we can find the confidence interval for nu1 minus nu2 for sigma 1 square and sigma 2 square. Both are known but not same, right? So that's what we are going to do, guys. So just like our previous case, I mean to say last lecture, we are going to see the same thing over here. So let me start with this one article. You can say 9.8. Article 9.8, that is two samples, two sampling estimation, and the difference between two means. That is two samples, two sample, or you can say sampling estimations, and second thing is difference between two means, difference between 2 means. So that's what we are going to see over here. And as I told you that nu of x1 bar minus nu of x2 bar, that is equal to, of course, nu1 minus nu2, because we proved this one, nu x bar, that is equal to nu1. So nu x2 bar equal to nu2, just article 9.34. So difference nu x1 by minus bar, nu x1 bar minus nu x2 bar, that is equal to nu1 minus nu2. That is easy to see. And we have this sigma now x1 bar minus x2 bar, or you can say, yeah, x2 bar, that is equal to square root of sigma 1 square over n1 square plus sigma 2 square over n2 square. You know this thing in my previous case, z equal to x bar minus nu divided by sigma over square root of n. That is my central limit theorem. But for these two cases, what we are having, so according to this one, now I have to adjust my z. So that is not x bar, but I would say that is x1 bar minus x2 bar and minus nu1 minus nu2 minus nu1 minus nu2, and my sigma over n, that is replaced by this one. So I would say that square root of sigma 1 square divided by n1 square plus sigma 2 square divided by n2 square. Sigma 1 square divided by is not actually square, sigma 1 square divided by, because square root of n, right? So yeah, square root of n, so n remains the same. There is no power, but because here we are taking this one under the square root sign, so that's why we are making square here. So actually my bad. Okay, so it is sigma n1 and sigma n2, but no square. Sigma n1 and sigma n2, but no square. So let's remove that part here. So we will have some clear n1 and n2 and n1 and n2. Just like the previous case, I mean to say, last talk, you know this thing, this fall between negative z alpha 1 to z alpha 2. These are normally distributed, and this is z alpha by 2, and this is negative of z alpha by 2. It falls between this one, right? Between this one. So naturally, this is nothing but, because this is nothing but your alpha by 2. This one is nothing but, this area is alpha by 2. So this area, total area is 1, so it is 1 minus alpha. That means whatever you have that lies between the probability of, you can write negative of z alpha by 2 is less than z is less than z alpha by 2, and that is equal to 1 minus alpha, right? If I plug this value of z over here, if I plug this value of z, I'm going to get that is equal to probability of negative z alpha by 2 is less than x1 minus x2 bar minus nu1 minus nu2 divided by sigma 1 square divided by n1 and sigma 2 square divided by n2 and square root sign, and that is less than z alpha by 2, and that is equal to 1 minus alpha. If you do this thing, you are going to get, just plug this value, whatever you have, just multiply throughout. Let me put big brackets to understand the concept. So this implies that I can write probability of negative of z alpha by 2, probability of negative of z alpha by 2, and here it is, I can multiply by this one, sigma 1 square by n1 plus sigma 2 square by n2, and that is less than or equal, that is less than x1 minus x2 bar, and here it is nu1 minus nu2 minus sign, and that is less than, here it is z alpha by 2, it is z alpha by 2 and square root of sigma 1 square by n1 plus sigma 2 square by n2, and that is equal to 1 minus alpha. You know that I don't want this part, I'm interested in nu1 minus nu2, so let me remove this one, so I can write negative of x1 bar minus x2 bar, and I can write over here negative of x1 bar minus x2 bar and plus sign, right? Because I have negative sign, so let me multiply throughout by negative sign, so this will be plus, this will be plus, is converted to greater than now, and this is converted to, this negative will be now positive, this is converted to again greater than, so this will be gone and that is greater than, and this negative will be now positive, this negative will be positive. If I write the same thing in a reverse order, that means this part first, so that is equal to, this implies that probability of you can write probability of, yes please, x1, and if you multiply by negative, this has to be negative, right? This is negative. So it is now x1 bar minus x2 bar negative z alpha by 2 and square root of sigma 1 square by n1 plus sigma 2 square by n2 is less than nu1 minus nu2 and is less than x1 bar minus x2 bar plus z alpha by 2 and square root of sigma 1 square by n1 plus sigma 2 square by n2, and that is equal to 1 minus alpha. If you, this is actually capital X, but if you write, if you remove this one and this one, so whatever you have here, whatever you are having here, starting from here to here, this is nothing but your confidence interval, where z alpha by 2 is the z value leaving an area of alpha by 2 to the right. So z value, z alpha by 2, you can see here from here to here, z alpha by 2 is the z value, leaving an area alpha, or you can say alpha by 2 to the right, right? Alpha by 2 to the right, and that's why we subtract from this one. So this is nothing but your confidence interval. So whatever the blue line I drew over here, that is your confidence interval with, you can see over here, sigma 1 and sigma 2, they are different and known. Sigma 1 and sigma 2, they are different and known. So that's how we can prove this one. And now, without wasting time, I just would like to go for the examples. So let me just save this one. Once I, save in a folder. Okay, so once I save this one, then after I can now go for, let me clear this drawing. And now I can go for book again. So book says that example number 9.10, a study was conducted in which two types of engines A and B were compared. Gas mileage in miles per gallon was measured. Gas mileage in miles per hour was measured. 50 experiments were conducted, look at over here, using the engine type A, and 75 experiments were conducted using the engine of type B. So two engines, N1 equal to 50 for first engine A, N2 equal to 75. I told you N1 and N2 could not be same every time, so they could be different too. The gasoline used and other conditions were held constant. The average gas miles was 36 miles per gallon for average, means mean nu1 equal to 36 for engine A, and 42 miles per hour, nu2 equal to 42. Find 96% of the confidence interval on nu B minus nu A, where nu and nu B are population means gas mileages for engines A and B respectively. Assume that the population standard deviation are 6 and 8. I told you given and different, and A and B normally distributed, that is already given to you. So we know this thing, that the only thing is we have to be careful about 96%. So let me just, this is the first example. So we are going to use again the same thing. Z score means Z table means normal distribution table, that is table A3 on the back of the book. So table A3, let me stop sharing this book now because we have all the data, and I can start again sharing my whiteboard. So article, I mean to say 9.10 example 9.10 says that I have, yes, nu b minus nu a and mean value. So first of all, xb minus xa, because it is asked to us in the form of nu b minus nu a. That means I have to have xb minus xa, and that is equal to 42 minus 36, and 42 minus 30, that is equal to 6. Okay, sounds good. And okay, what are the other conditions provided to us? N1 equal to 50 and N2 equal to 75. So let me just write it down over here that N1 equal to 50 and N2 equal to 75. Okay, sounds good. And standard deviation, that is sigma 1, that is provided to us. Sigma 1 is equal to 6 and sigma 2 is equal to 8. Whenever I write N1, that is with engines with respect to sigma 1 and with respect to engine A, and this is nothing but that is with respect to engine B. This is engine A, engine B, and this mean value, this is for B and this is for A. Okay, so that's what it means. Good. Now it says 96%, 96% means 0.96. That means 1 minus 0.96, that is equal to 0.04. That is your alpha value. As now, just now explained to you, this is your alpha by 2, and this is your alpha by 2. So alpha by 2, that is equal to 0.04 divided by 2 and 0.02. So this region alpha by 2, that is equal to 0.02. Now, if you take 1 minus 0.02 alpha by 2, that is equal to 0.98, right? So 0.98, or you can say 0.988. You can add this to 0, and then after you go to table A3, and in this table, whenever you find, because here you are given like this, and somewhere over here you will find 0.9800, or approximately this point. And that approximation, that is nothing but, if you look at the table 2.05, that means I can write Z alpha by 2, that is equal to Z alpha by 2 is 0.02, and that is equal to 2 point. This value corresponds to 2 point, as I told you, 0.5 in the table A3. So it is 2.05. Once you have this alpha by 2, then after I can plug the values, that is x1 minus x2 bar and minus x1 minus x2 bar and Z alpha by 2 and square root of sigma 1 square over n1 plus sigma 2 square over n2 is less than nu1 minus nu2, and or here in this case it is nu b minus nu a, right? Nu b minus nu a, because you have to have this order. It is asked to you in this order, and that is less than x1 bar minus x2 bar and plus Z alpha by 2 and square root of sigma 1 square by n1 plus sigma 2 square by n2. So this implies that you can write 6 minus, here it is 2.05, and sigma 1 square and sigma 2 square, sigma 1 square, that is equal to 42, and sigma b equal to, what is my b? B is equal to, you can see, that is equal to sigma 1 square. Sigma 1 square is, what is my sigma? 8, right? So sigma 1 square, that I'm sorry, that is equal to, this corresponds to, you have to have B over here. So better to write over here sigma B and sigma A and NB and NA, just for the sake of convenience. Here also you can write sigma B and sigma A and NB and NA, just to avoid the mistake. So here it is sigma 2 is 8, or you can write sigma 2, and that is nothing but sigma A, and this is nothing but sigma B. So sigma B is 8, and the square root of 64 divided by 75 plus 36 divided by 50, and that is less than nu B minus nu A, and that is less than 6 plus 2.05 and square root of 64 by 75 plus 36 by 50. Use your calculator, you're going to get that is equal to 3.43 is less than nu B minus nu A, and that is less than 8.57. That is less than 8.57, and that's why we can say what was asked to us, find the find the 96% of the confidence interval. This is the 96% of the confidence interval, this 3.43 to 8.57, all your values. This is this line, whatever you figure it out. So that is the confidence interval. So negative 3.43 to 8.57. And this is your 96% of the confidence interval, right? Whatever the data are provided to us, they are correct up to 96%, and they are lying between 3.43 to 8.57. That is the meaning. So now I saw, this is the example I solved with the known variance, and now I'm going to solve the example with unknown variance. Again, if you have unknown variance, but again, they are divided into two parts. Unknown variance, they are equal. Unknown variance, they are not equal, right? So unknown variance equal. So let me, whenever unknown variance equal, you are good. I mean to say unknown variance equal, the sigma 1 square and sigma 2 square, they are just sigma square. But if they are unequal, in that case, you have to stay with different sigma 1 and sigma 2. Okay, let me again save this file and let's go to the book and let me clear the drawing and let's go for, as I told you, my book is over here. So you can see over here, guys. Now I'm not going to prove everything every time. If you are see, they are unknown, sigma 1 and sigma 2, they are unknown. Unknown means definitely we have to rely on t distribution, chi-square distribution. Okay, that is one thing, but they are same. If they are same, that means sigma 1 square equal to sigma 2 square. So whatever I had previously, sigma 1 square, and say that is equal to sigma square, you can pull it out. So sigma square, you can take it out of the square root sign. So it is something like this, right? And n1 minus n2 s1 square over sigma square. This is the formula you can get from the previous chapter about the random variable. So n1 minus n2 square s1 square by n, this is have the chi-square distribution with n1 minus 1 degree of freedom and n2 minus 1 degree of freedom, because chi-square distribution, t distribution, always you have to have the degree of freedom because sigma is unknown, and degree of freedom is always nothing but n minus 1, because you have here two companies like this, or two sampling distributions. Because of two samplings, you have two populations, I mean to say samples, and that is nothing but one is n1 and second one is n2. So here it is n1 and n2 like this. So chi-square n1 minus 1 and n2 minus 1 degree of freedom respectively, and further they are independent chi-square variables. I told you that they are independent since the random variables were selected independently. So v is nothing but my n1 minus 1 over sigma 1 square plus n2. So whatever I have, according to theorem 8.4, whatever I have, I just would like to write it down in terms of, because theorem 8.4, that was for unknown sigma, right? And unknown sigma means chi-square distribution. And we did this thing in theorem 8.4. So that's why I don't want to repeat the same thing, but I just would like to let you know this thing, that we are using the same thing, but one is for your sampling n1 and second one that is for n2, and accordingly we defined our v, and our v that is in this form because we have to add both of these. And once you add this one, and if you go for the common sigma, so it is n1 minus 1 square and s1 square, n2 minus 1 s2 square, and whatever v you have, you know that t is nothing, capital T is equal to z divided by v. If you again look at theorem 8.4, t is nothing but z square divided by v. V is this one, just plug this v over here, right? V is this one, and that's what we did over here. So t equal to z divided by v, and z divided by v, that is, this is my z, this is my z, look at over here, this is my z, x1 minus x2 bar minus, so this is my z, divided by v, v is this one, so n1 minus 1 s1 square, n2 minus 1 s1 square addition, and divided by sigma square, right? So t divided by v, and that is equal to, yes, z divided by v, yes, z divided by v, so that is equal to this one. Okay, sounds good. And this estimation you can get, actually it is z divided by sp, but this estimation you have to get, this leads us to this discussion, full estimation of variance is S1, SP square equal to this one. No one is going to ask you how this formula is derived. Just keep in mind this thing that your T, if you plug this value over here, SP square, or SP square is N1 minus 1 S1 square. There is this one minus this one and N1 plus N2 minus 2. So if you take this sigma square out, it is simply sigma out because of the square root sign. And this you can write it down in terms of SP square, right? This you can write it down in terms of SP square. So this SP square actually is nothing but, and this sigma square, you can pull it out. So this sigma from here will get cancelled out. This is nothing but your SP square. So your SP square that is out of the square root sign will be simply SP. And that's the reason we are getting over here SP and N1 and N2. So this is my final form. So just keep this thing in mind. Just forget all these derivations. Just look at this one. This T equal to for sigma 1 and sigma 2 unknown but equal. Your T will be x1 minus x2 bar minus nu1 minus nu2 and SP square root of 1 over N1 plus 1 over N2. And exactly same as article 8.4. Now T, or I would say article 9.3 and 4, and just now we did for known sigma, exactly same probability of negative, but not Z. Now T negative T alpha by 2 is less than T alpha by 2 and 1 minus alpha. Plug this value over here. Once you plug this value, we are looking for nu1 minus nu2. So multiply throughout this expression by denominator. Once you multiply throughout by denominator, you're going to get this one will be here and here, right? And then after you can add or you can subtract x1 minus x2 throughout. Because of the negative sign, just change the sign. Just now we did this thing on our first slide, and finally you are ending up with this estimation. See, this is not this estimation, but this is what you are doing. And finally you are looking for nu1 minus nu2. So you are ending up with this estimation. So x1 minus x2 bar, x1 bar minus x2 bar minus T alpha by 2. Instead of Z, now you have T and SP. This is slightly different. And this is SP. SP is given by this one, N1 minus 1 S1 square, N2 minus 1 S2 square, N1 plus N2 minus 2 in denominator. So that is my SP, nu1, and exactly. So that's the difference. SP over here and here, there is no sigma you can see over here. So if x1 bar and x2 bar are the means of the independent random variables of size N1 and N2 respectively, from approximately normal population with unknown but the equal variance, 100 minus 1 minus alpha percentage confidence interval, you know this thing that is always given by nu1 minus nu2, and that lies between this one and this one. Here, because I have two variants, 2 N1 and N2, so my degree of freedom will be N1 plus N2 minus 2. Actually, it is N1 minus 1 plus N2 minus 1. So it is N1 plus N2 minus 2, right? And this area alpha by 2, that living an area of alpha by 2 to the right. So we are going to follow the exactly same process. Now let's start the example. Okay, guys. So there is same kind of thing, and that's why I did not derive. If somebody is interested, he or she can go for this one. But please keep this thing in mind that this is this SP and square root of 1 over N1 plus 1 over N2. There is nothing but the estimated standard error. In the previous case also, this part was the estimated standard error, and same over here, this is the estimated standard error. So if somebody is looking for the error, just keep this thing in mind that this one is nothing but not by this starting from SP, and this one is just starting from SP and the right side, not the, that is your estimated standard error. Exactly same thing, whatever we did in my previous case. Whatever we did in the previous case, look at here. For this case, yes, this one was also here Z alpha by 2, and this one that was the estimating standard error, right? Same thing is over here too. Okay, guys, so let's continue with the example number 9.1. This first paragraph, that's just the information. If somebody is interested, can read this part, but I would like to start with here. 2 independent sample stations were chosen for the study, one located downstream from an acid mine discharge point and the other located upstream. For 12 monthly samples located at the downstream station, the species diversity index had a mean value x1 bar equal to 3.11 and standard deviation s1 equal to 0.7, s1 sample standard deviation, right, 0.771. While the 10 monthly standard samples collected at the upstream station had a mean index value x2 bar equal to 2.04 and the standard deviation of s2 equal to 0.448. Find 90% of the confidence interval for the difference between the population mean for the two locations, assuming that the population are approximately normally distributed with equal variance. Right, guys? So they are, see, equal variance, this word is being introduced. This word is being written down over here. That means your sigma 1 and sigma 2, they are not known to us, rather than we know S1 and S2. But this sigma 1, they are not known, but they are equal. Right? It could be possible in some practical examples that they are equal. Sometimes they are non-equal. But here it's an example for unknown sigma 1 and sigma 2, but they are equal. Right? Sigma 1 and sigma 2, they are same, equal, but unknown. Okay, we have all these data. Let's keep these data in mind and try to solve our next example. So let me just help you guys for this one. So let me stop sharing this one and let me again go back to my whiteboard. So probably idea will be more clear if I write it down over here on the whiteboard. So first of all, example 9.11, it says that let nu1 and nu2 represent the population means respectively for the species diversity indicates at the downstream and the upstream station. We wish to find 90% of the interval for nu1 and nu1 minus nu2. Okay, so first of all, my x1 bar and x2 bar, right, that is equal to actually nu1 minus nu2. That is 3.11 minus 2.04 given to us, and that is equal to 1.07. We require SP square in the formula, and that's why let me just count this SP square separately. By definition, SP square is nothing but n1 minus 1, and here it is s1 square and n2 minus 1 and s2 square, n2 minus 1 and s2 square, and divided by n1 plus n2 minus 2, n1 plus n2 minus 2. n1 is nothing but we are given n1 is 12, n1 is 12, so I can write here 12 minus 1, that is equal to 11. S1 square is nothing but what is your S1? S1 is given to us, that is equal to 0.771. So S1 equal to 0.771. I'm looking for N2, and S2 is equal to 0.448. So 0.44 and 8. And X1 is equal to an S2 equal to this 1.448. Sounds good, guys. And N2 is equal to 10. N2 is equal to 10. Okay, so here it is 9. S1 square is equal to 0.771 square plus N2 is equal to 10 minus 1 is 9, and S2 is equal to 0.448 and square, and divided by N1 plus N2, that is equal to 12 plus 10 minus 2, that is equal to 20, right? So that is equal to, and if you use your calculator, you're going to get that is equal to 4, 1, and 7. Once you have this 4, 1, and 7, that is my SP square. So naturally, I have to go for SP is equal to square root of 0.417, and this 0.417 will give us 0.646, right? So 0.64 and 0.64 and 6. Okay, guys, now I have 90% of the confidence interval. So 90%, that is 0.90. 0.90, so 1 minus 0.90, that is equal to 0.1 or 0.10, you can say. And that is my alpha. So naturally, alpha by 2 is equal to 1 minus, 0.10 divided by 2, that is equal to 0. Here it is given. Do we really require alpha by 2 or just we want alpha? Let me just make sure. Nu1 and nu2. Okay, fine. So that is equal to alpha by 2. That is equal to 0.05 naturally. 0.05, right? Good. 0.05. Here equal to t equal to 1, and this is my n1, n2 minus 2. So my v is nothing but v is also n1 plus n2 minus 2, n1 plus n2 minus 12 plus 10, 12 plus 10 minus 2, that is equal to 22, minus 2, that is equal to 20. So my v is equal to 20 here. And this is alpha by 2. This is this one. So this is alpha by 2.005 and negative alpha by 2. Negative alpha by 2. You can say what, negative c alpha by 2. Okay. And this is equal to 1 minus alpha. And that's what we are looking for, the 90% of this one. Good, guys. So here it is alpha equal to some 1 minus 0.05, that is equal to 0.95. So you can write 0.95 and 00. And then again you can see now use table A4, because it is now chi-square distribution. So table A4, and this corresponds to, if you use your chi-square distribution, this will be corresponds to 1.725. So 1.725. That means I can write T alpha by 2, because now it is chi-square. So T alpha by 2, that is equal to T 0.05, and that is equal to 1.725. So I have my T alpha by 2 over here, and now I'm going to plug the values, because now I have everything with me. So my X1 bar, if you use your formula, page number 288, just now I showed you, I don't want to write the formula again and again. So it is 1.07 X1 minus X2. Minus T alpha by 2, 1.725. Then my SP is nothing but 0.646. So 0.646. And that is less than, and sorry. Then square root of 1 over n1, that is 12, and 1 over n2, that is equal to 10. And this is nu1 minus nu2, and that is less than 1.07 minus, plus 1.725. Here it is 0.646, and square root of 1 by 12 plus 1 by 10. 1 by 10. I think no need to write this bracket, right? Just remove this bracket. Okay, and 1 by 10. If you use your calculator, you are going to get that is equal to, this implies that 0.593 is less than nu1 minus nu2 is less than 1.547. 1.547. So this is your 90% of the interval. So your 90% of the interval, that is nothing but 0.593 to 1.547. So during this range, 90% of the given data are accurate. Now interpretation of the confidence interval. So for the case of single parameter, the confidence interval, this is important, guys. Just look at over here. Let me just save this file. So what we mean, actually we already went through this one, how to interpret the confidence interval, but here we have 2n1 and n2. So how we interpret this one, that's also in the similar way, but let me just go through this one. So let me clear this part. Let me stop sharing this one, and let me again start sharing my book. So it says that for the case of single parameter, the confidence interval simply provides error bounds on the parameter. Values contained in the interval should be viewed as reasonable values given the experimental data. In the case of the difference between two means, because now nu1 and nu2, nu1 minus nu2, the interpretation can be extended to one of comparing the two means, right? And for example, if we have high confidence that the difference nu1 minus nu2 is positive, we would certainly infer that nu1 is greater than nu2, right? Because nu1 minus nu2 is positive, nu1 is naturally greater than nu2 with little risk of being error. For example, previous example 9.11, just the previous example, we are 90% confident that the interval from 0.593 to 1.547 contains the difference of the population means for values of the species diversity index at the two stations. Right? In this example, we can interpret the result like this, that 90% of the confidence, we are 90% of confident that the interval from 0.593 to 0.147 contains the difference of the population means for values of the species diversity index at 2 stations. The fact that both confidence limits are positive indicates that on the average, the index for the station located downstream from the discharge point is greater than the index for the station located upstream. Why? Because both of them are positive. So index for the downstream, that is downstream, is greater than the index for the station located upstream. Right, guys? So that's how one can interpret the result. That's how one can interpret the result. So always, guys, keep in mind this thing that whenever you are solving the practical examples like this, you have to have answer in terms of the given example, in terms of the real life problem. You cannot leave the answer just like giving the interval, but you have to interpret your answer in terms of the questions, in which fashion it is asked to you. Okay, now the sample size, equal sample size. Previous example, N1 and N2, they were not equal. Keep in mind this thing, the sigma 1 and sigma 2, they are not same, unknown. Sigma 1 and sigma 2, right? Sigma 1 and sigma 2, they are equal, they were equal, unknown. But N1 and N2, both samples, they are separate, but they are different. But it could be possible that equal sample, you have some equal samples N1 and N2. The procedure for constructing confidence interval for nu1 minus nu2 with sigma 1 and sigma 2 equal to sigma unknown requires the assumptions the populations are normal, of course, slight departures from either the equal variance or the normality assumptions do not seriously alter the degree of confidence for one interval. Right? If the population variance are considerably different, we still obtain reasonable result when the populations are normal, provided N1 is equal to N2. And therefore, in planning an experiment, one should make every effort to equalize the size of the samples, right? If it is possible, try to equalize the size of the sample, because a procedure, the same kind of things, a procedure that is given, we are going to see in chapter 10, for testing the equality of two unknown population variance based on the information provided by the sample variances. So just keep this thing in mind. So because of course they are not same, but if it is possible, try to make them as close as possible, or try to make them equal just for the better estimation. Okay, so now the last part is left out, that is the unknown. Of course, variance are unknown, and we went over unknown variance with, but they are equal, but now unknown variance and they are not equal, unequal variance, unknown and unequal variance, right? So whenever unknown and unequal, see, previously it was just a known part, and that's why I used my t equal to x1 bar minus x2 bar nu1 minus nu2 and sp, that was outside, and 1 over n1 plus 1 over n2, right? Now they are not same. That means now I have to have something, some s1 square and s2 square separately. And that's why I would like to denote by t dash because of this difference. So my t dash over here, that is given in this form, and my degree of freedom will be different. Previously, degree of freedom was just n1 plus n2 minus 2. But now degree of freedom will be just such a big expression, and one has to keep this thing in mind. Without this one, you cannot solve the example, because ultimately you are looking for that degree of freedom you are using to get the t distribution, means a probability, using table A4. So t distribution, here it is given in this form. V equal to s1 square over n1. Previously it was so simple, just n1 plus n2 minus 2, but now it is such an awkward form. So please be attentive. And again, we are going to do the same thing, that probability of negative t alpha less than t dash. Now it is t dash, and less than t alpha by 2 is approximately equal to 1 minus alpha. Just plug this value over here for t dash and go for the equation of nu1. Go for the nu1 minus nu2 over here in the middle part, just by using some algebra stuffs. So finally, we are ending up with x1 minus x2 bar minus t alpha by 2, square root of this one. Now it is not sp, just s1, s2 goes, they go inside, same here. And this is again nothing but the estimated standard error, because as I told you, you have to have some standard error. So this is your estimated standard error. This one, estimated standard error, and this one, estimated standard error. Just this one, not negative T alpha by 2. Please keep this thing in mind. Right, guys? And that's what mentioned over here. So confidence interval for nu1 minus nu2, sigma 1 square and sigma, they are not equal. They are not equal. When they are unknown and not equal, I would say other way around. Right, guys? And let's go for the last example of this chapter. And then if next time we are going to start the last chapter, that is chapter number 10. And we would consider this as the syllabus for this probability and statistics course. Number of chapters are there in this book, but other chapters are being studying in. Other chapters we are going to study in our next higher level statistics course. But we covered lots of things over here. And let me just start with this last example. With the things in mind that we are going to use this confidence interval and we are going to use this degree of freedom. And whatever alpha by 2, this is the living an area to the right of alpha by 2, right? This degree of freedom, living an area, alpha by 2 to the right. Okay, so example 9.2 says that a study was conducted by the Department of Zoology at Virginia Tech to estimate the difference in the almost of the chemical orthophosphorus measured at 2 different stations on the James River. Orthophosphorus was measured in milligrams per liter. 15 samples were collected from station 1 and 12 samples are obtained from station 2, N1 and N2, right? 15 and 12. The 15 samples from station 1 had an average orthophosphorus content of 3.84 milligrams per liter and standard deviation 3.07 milligrams. That is, S1 is given to you. While 12 samples from the station 2 had an average contained 1.49, that is your X2 bar, right? And milligrams per liter, and the standard deviation is 0.80, that is equal to S2 milligrams per liter. Find 95% of the confidence interval, right, for the difference in the true average orthophosphorus contents at these 2 stations, assuming that the observations came from the normal population with different variances. Okay, guys, sounds good. And now the confidence interval based on this one, before I start this one, I just would like to give you one more thing, that what we mean by the confidence interval. So here X1 bar minus X2 bar, right? The confidence interval estimation. Confidence interval estimation is this one. Starting from here to here, this is your confidence interval estimation. Confidence interval, but it is plus and minus sign. Plus and minus. So this one and this one. So actually this and this, same thing. Ultimately same thing. The point estimation, whatever is explained to us over here, is exactly same thing. So this is the confidence, I would say, with plus and minus sign. So minus sign for this one, plus sign for upper bound, like this, and that is called the confidence interval estimation. And confidence interval estimation for T alpha by 2, unknown sigma, and Z alpha by 2 for known sigma. And here in this case, yeah, X1 minus X2, that is equal to this one, S1 bar, and that is very simple. I think it's not required. Let's focus on the example. Okay, so I have all this data. So let me use this data to get the solution of this problem. So let me again stop this book, and let me start sharing you my white screen. Okay, so for station S1, you know this thing, example 9.12 for station S1. So I can say station 1 and station 2. I have my X1 bar that is equal to 3.84. I am given S1 is equal to 3.07. I am given N1 equal to 15. For station 2, I am given my X2 bar is equal to 1.49. My S2 is given, that is equal to 0.80, and my N2 that is equal to 12. right? 95% of the confidence interval, that is equal to 0.95. So 1 minus 0.95, that is equal to 0.05. You know this thing, we did this thing so many times, alpha. So alpha by 2 is equal to 0.05 divided by 2. So it is 0.025. Am I right? 0.025. And we are looking for T alpha by 2, that is equal to T 0.025. 0.025. 0, 2, and 5, right? 0.02 and 5. And that is equal to, this is with, what is my degree of freedom? So my V is equal to, we have to make sure about this thing first. So my V is nothing but, so first of all, let me find my V here. Using this data, my V is equal to, so V is S1 square divided by N1 plus S2 square divided by N2 and whole square. It says something like this. And whole divided by, you can see here it is S1 square divided by N1. S1 square divided by N1 whole square, whole divided by N1 minus 1. Whole divided by N1 minus 1. Right? Plus S2 square divided by N2 whole square and whole divided by N2 minus 1. N2 minus, and bracket complete. If you plug the values over here, you'll get that is equal to 3. Just take the value 3.0707 n square divided by N1 equal to 15 plus I have 0.80 n square and divided by N2 is equal to 12 and whole square and whole divided by here it is S1 square. So it is 3.07 square divided by N1 is equal to 15 and whatever you're going to get, that is square, and whole divided by N1, that is equal to 15 minus 1, that is equal to 14, plus here it is 0.80 square divided by 12 and whole square and whole divided by N2 equal to 12. So 12 minus 1, that is equal to 11. If you use again your calculator, you're going to get that is equal to V is nothing but approximately 16.3. I told you that you have to have your V as an integer, right? So approximately I would say 30. Always round the number. So round it. Whenever it is some decimal, just avoid them because degree of freedom is always the integer 1, 2, 3 like this, or positive integer, I would say. It would not be any fraction or any kind of decimals. So you have to round it, right? So here I have rounded this number and that is equal to this one. So with V is equal to now 16. If you look at this one table A4 and suppose V equal to 16, you're going to get somewhere over here. V equal to suppose 16 and this is my V and my alpha somewhere over here that is equal to 0.025, right? So V equal to 1 and 0.025, whatever the number you are going to get, that is nothing but your probability in your table, and that probability I have found over here, that is nothing but 2.120. So 2.120. Once you have this T alpha by 2, then plug all these values in my formula. So 2.35 minus 2.120, and the square root sign of 3.07 square divided by 15 plus 0.80 square divided by 12, and that is less than nu1 minus nu2, and that is less than 2.35 plus 2.120 and square root of 3.07 square by 15 plus 0.80 square divided by 12, and use your calculator and you're going to get that is equal to 0.60 is less than nu1 minus nu2 and is less than 4.10. Right? So 0.6. So 95% values are lying between this 0.60 and 4.10, between these two values. Right? And that means we can say that the 95% of confidence that the interval from 0.6 to 4.10 milligrams per liter contains the difference of the true average orthophosphorus contains for these two locations, right? I repeat, the interpretation of the problem is like this. Because we are getting 0.60 is less than nu1 minus nu2 is less than 4.10 is less than, let me write, 4.10. I would say that the interval from 0.60 to 4.10, 0.60 to 4.10 milligrams per liter contains of the difference of the true. By difference, it is nu1 minus nu2. So difference of difference of the true average, difference of the average orthophosphorus contains for these two locations. Contains these two locations, right? So that is the interpretation. And let me save this part again. Let me save this one. And now I think let's solve some of the examples given to you in your exercise. So I would like to go for some exercise problems. Let's start with the first one. Let's go for a few problems and then we end. That's the end of today's class. So let me just minimize this one, that already I saved this one. So in the folder, and now clear the drawing. And let's go for, let me stop sharing this one and let's go for the book. So if I want to again share my book with my problems, the first problem, 9.35. A random sample of size n1 equal to 25 taken from a normal population with a standard deviation sigma 1 equal to 5, sigma is known now, has a mean x1 equal to 80. The second random sample size n2 equal to 36 taken from a different normal population with a standard deviation sigma 2 equal to 3, sigma 2 and sigma 1 both are known to us and they are different. Right, has a mean x2 bar equal to 75. Find the 94% of the confidence interval. So again, z-score. Okay, guys, just keep this thing in mind. And I just would like to share my whiteboard to solve this example. So example 9.35 says that example, random sample size of n1 equal to 25. Okay, so 9.35 exercise. 9.35. So I would say that n1 equal to 25, then n2 equal to 36. I have x1 bar is equal to 80. I have x2 bar. If you read the example in the book, I have x2 bar that is equal to 75. I have my sigma 1 is equal to 5. I have my sigma 2 is equal to 3. Okay, and it says how much percentage? 94%. 94% that is equal to 0.94. So 1 minus 0.94 that is equal to 0.06. And this is my alpha value. So alpha by 2 equal to 0.03. 0.03 and 1 minus 0.03 that is equal to 0.97. So 0.97. That means if I go for z alpha by 2, so that is equal to z 0.03, and z 0.03, if you go to table A3, this 0.97 that lies somewhere over here, 0.97, you can write 9700, and you can go for some approximation. If that lies between 0.005 and 0.05 and 0.06, you can write 0.055 like this, right? Suppose here it is 5 and 6, 0.05 and 0.06, and suppose your value lies over here, it is 0.55, something like that. But you can always take the mean average value. So here it is for 0.03, and that value is nothing but, if you look at the table, that value is nothing but 1.88. So 1.88. So you're going to get here 1.8, and here it is 0.8. So 1.8 and 0.8 matches this value in table 3. So 1.88, and then plug the values in your formula. So 80 minus 75, you know the formula, minus 1.88 and square root of what, how much it is? 5 sigma 1 square, that is equal to 25 sigma 1 square, right? That is equal to 25, and my n1 is equal to 25. Good. So it's simply 1 plus 9 divided by 36, that is less than nu1 minus nu2, and that is less than, yes please, 80 minus 75 plus 1.88, and square root of, yes, 25 divided by 25 plus 9 divided by 36. Same thing, only differs by plus and minus sign. So this implies that 2.9 is less than nu1 minus nu2, and that is less than 7.1. So this is your confidence, 95% of the confidence interval. You can see over here. Here you can see my sigma 1 and sigma 2 are known. Sigma 1 and sigma 2, they are known. Right, guys? Okay, so now I would like to go for one more example, that is example number 9.37. 9.37, then we'll go for 9.40. Let's see. So let me just read the example 9.37. If it is a similar kind of example, then we can skip, but let me just go for this one. So, let me just and clear the drawing. Okay, and stop sharing, and let's share a book. So 9 as I told you, 37. A study was conducted to determine if a certain treatment has any effect on the amount of metal removed in a pickling operation. A random sample of 100 pieces were immersed in a bath for 24 hours without the treatment, yielding an average of 12.2 millimeters of metal removed, and a sample standard deviation is 1.1 millimeters. A second sample of 200 pieces were exposed to the treatment, followed by the 24 hours immersion in the bath, resulting in the average removal of 9.1 millimeters of metal with a sample standard deviation 0.9 millimeters. Compute 98% of the confidence interval. Okay, does the treatment appear to reduce the mean amount of metal removed? So that's what it says. Okay, guys, just keep these data in mind and let's solve this example, right? It says that we want to find the confidence interval. See, every time you don't have to write the big formula, because left and right side of nu1 minus nu2, they differ just by plus and minus signs. You can write plus and minus. I can do that example right now. Okay, so stop sharing this one and let's start sharing the example number 9.37. So exercise 9.37. Okay, guys, so 9.37 says that my n1 is equal to 100, my n2 is equal to 200, x1 bar is equal to 12.2, x2 bar is equal to 9.1, S1 is 1.1, because you can see over here my sigma 1 and sigma 2 unknown in this example. That is equal to, and that's the reason I took this example, S2 is nothing but 0.9, and we have 98% of the confidence interval, so that is equal to 0.98. So 1 minus 0.98, that is equal to 0.02, and that is my alpha. So alpha by 2, that is equal to 0.01. So 1 minus 0.01, that is equal to 0.99. And 0.99, so z alpha by 2, that is equal to z 0.01, and that is equal to, right? So 0.99 means 0.9900. Again, use table. Now you can use what? Is it z or it is t? It has to be t, right? No z, because sigma 1 and sigma 2, they are not known to us. So I think I need to go for t distribution. Okay, so sigma 1 and sigma 2 both are unknown, so it has to be t distribution. Okay, guys, sounds good. So let me just solve like this. It's not z, but it is t. So let me erase this one. Okay. So T alpha by 2 that is equal to 2 is 0.01. My N1 and N2 that is equal to this one. So N1 plus N2 minus 2 that is equal to 100 plus 200. Oops, these values are not given to us, right? So that is equal to, I can find this value. Page number, let me see, just let me look at the definition, page number 290. And that is for the page number 290, the definition is given to us. The confidence interval is given to us x1 bar minus x2 bar. Okay, sounds good. Good, guys. So let me look at my table. My table is here. Table is here and page number 290, my degree of freedom V degree of freedom, because now both are unknown, sigma 1 and sigma 2 both are unknown and they are not equal, right? So we are going to use this table, and sigma 1 and sigma 2, they are not equal, unknown and not equal. So my degree of freedom will not be given like this. Degree of freedom will be different now. I mean to say that how can I find my degree of freedom? We have to be very careful finding the degree of freedom, because my N1 and N2, I have to just make sure, give me 1 minute, guys, because here it is N1 and N2 and my samples are, okay, good. Yes, so sigma 1 and sigma 2s are not given, but instead of that, we are given this part. Sounds good. Okay, so if you use here your degree of freedom, that is V is equal to, so V is equal to S1 square divided by N1 plus S2 square divided by N2 and whole square and divided by S1 square divided by N1 and whole square divided by N1 minus 1 plus 1 bracket and second bracket S2 square divided by N2 and whole square, this is N1, divided by N2 minus 1. And if you use this one, if you plug these values, and you're going to get one number, right? I have not calculated that one, but you can definitely, you're going to get that number. Using that number, you can find this value. I think the number you're going to get over here, that is something, something like 15, 16, something like that. So use that number over here. But I calculated this value, and this value is nothing but 2.327. So 2.327, right? 2.327. That is my T 0.01. Now I'm going to plug this value in my formula x1 minus, or x1 bar minus x2 bar. This is actually nu1 minus nu2 is equal to, you can say, and plus or minus T alpha by 2. And here it is square root of S1 square by N1 plus S2 square by N2. S2 square by N2. So if you plug the values over here, you're going to get that is equal to 12.2 minus 9.1 plus or minus my T alpha by 2 is 2.327. Just now I figured it out. See, you can write like this, plus and minus if you want. Just if you don't want to write the whole expression, otherwise you can go for the whole expression given to you on page number 290, first equation. And S1 square is nothing but my S1 is 1.1. So 1.1 square, and N1 is nothing but 100. And my N1 is 100 and S2 is nothing but, what is my S2? 0.9 square and divided by 200. And if you estimate this, we're going to get 3.1 plus or minus 0.30. Right? And that means it is, if you take minus sign, you're going to get 2.80, and nu1 minus nu2 is less than 3.40. So this is your 98% of the confidence interval. 98% of the confidence interval, you can write like this. right, guys? Okay, guys. So that's how you can solve example 9.37. And again, let me save this one and let's go for the next example. So save this one in a folder and let's clear the drawings. And now let me stop sharing this one and let's go for the another example. And that example is which one we can go over. I think all the examples now, they are almost same, but let's go for just one more and let's stop. That is 9.40. 9.40 and 41, they are equal, almost same. So if I solve 40, you can solve 41 by your own very easily. So please do that thing, right? And let me solve just 940, and that is, I think, more than enough. We'll stop over there. So 9.40, that is this example. 41 is exactly same, but now instead of, see, we are not given any kind of new value, means new one, new two, or sigma 1, sigma 2, S1. They are not given, but we are given some data. So usually, practically, we are getting some data from the real life problem, and accordingly, we are going to take help of chapter 2, 3, and try to find your new, then sigma, whatever it may be, if it is known or unknown, accordingly you need to find. And then after we can apply this chapter 9 results, whatever we went through. Okay, example number 9.40, the last one. It says that in a study conducted at Virginia Tech on the development of ectomycorrhizal, a symbiotic relationship between the roots of tree and the fungus, in which minerals are transformed from the fungus to the trees and the sugars from the trees to the fungus. 20 northern red oak seedlings exposed to the fungus given over here were known in a greenhouse. All seedlings were planted in the same type of soil and received the same amount of sunshine and water. Half received no nitrogen at planting time to serve as a control, and the other half received 368 ppm of nitrogen in the form of NaNO3, right? Sodium nitrite. The stem weights in grams at the end of 140 days were recorded as follows. Some record, no nitrogen, right? And nitrogen. That stem weights are given over here after 140 days. Construct 95% of the confidence interval in the mean stream weight between seedlings and that receives no nitrogen and those that receive 368 ppm of nitrogen. Right, no nitrogen and 368 ppm of nitrogen. Assume the population to be normally distributed with equal variances. Okay, guys, so last example of this chapter. And let's start with example number 94, exercise problem. (9.40). Okay, guys, so we are given N1 is equal to 10, N2 equal to, again, 10, yes, N1 and N2, they are same. X1 bar is equal to 0.399. X2 bar mean is 0.565. This is not given to us, but whatever is given to us, that is 0.30, then plus 0.53 plus 0.28, this plus blah 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 up to 0.43. These are the data divided by 10, and that is nothing but my X1 bar. This is for no nitrogen. Same way you can find for the nitrogen, and that's what I did. That's what I'm finding 0.399. So that's how this value is not given to us, but this value you can get like this. Exactly same way, my X2 you can find like X2 bar is equal to 0.26 plus 0.43 ... Finally 0.46 divided by How many observations? 10 observations. And that value is nothing but 0.565. And that's what I did here for you guys. Okay. So x1 bar and x2 bar. Now, naturally, I can find my S1. So SP is nothing but, or S1. S1 is nothing but, how can I find my S1? Now, S can be found by 1 over n minus 1. That is my S. 1 over n minus 1 summation of, this is from formula page number 248. Page number 248 formula, I would say that, which chapter? Page number 248, that is chapter number 8. Page number 248, before T distribution, this formula is given to you, degree of freedom of a measure of sampling information. 248, sorry. Yes, corollary 8.1. Corollary 8.1, this x bar and s square formula is given to us. Corollary 8.1. Page number 241, COROLLARY 8.1. According to this one, I have a formula summation of, here it is, xi minus x bar and square. I runs from 1 to n. Here in my case, it runs from I is equal to 1 to 10. And here it is S1, so I would like to write N1. Actually, as N1 and N2, they are same, but X1 bar, X1, Xi and Xi bar, they are not same. Look at over here. So you have to calculate both the things separately. I have used this formula. I'm not going to calculate here, but because already we did this thing so many times in chapter 4, chapter 8. So use this formula and you are going to get that is equal to my S1. So this implies that S1 is equal to what I found, that is equal to 0.07279. And exactly same way by using this data, I'm going to find my S2 that is equal to, in S2, I'm going to write only here S2. Here it is N2 is of course 10 minus 1 is 9, but data are coming from here. Then I did this thing for you guys that is equal to 1.289. So I have my S1 and S2. I have all these datas with me. So now I think I can now go for my SP, right? So what is my SP now? So SP is nothing but, yes, please guys, N1 minus 1 S1 square plus N2 minus 1 S2 square divided by N1 plus N2 minus 2, right? N1 plus N2 minus 2. Okay, SP is equal to this one. And if you use this one, if you just plug the values S1, S2, whatever you got over here, if you use this one, you're going to get 0.14172. So I found my SP also. I found my SP. And now I'm going to take care of the formula. The formula over here, that is nothing but page number 288, right? So formula is on page number 288, where sigma 1 and sigma 2, because it is given over here that sigma 1 and sigma 2, they are same, right? Because if you read the formula, where is the problem? Yes, if you read this one, you are going to get construct 95% confidence interval between the mean and the standards. No nitrogen, those 30 ppm, assume the population standard is with equal variance. If you look at the last line, equal variance is being mentioned in the example. Because the variances are equal, means sigma 1 and sigma 2, they are same. Sigma 1 and sigma 2, they are same. Sigma 1 is equal to sigma 2, but both unknown. Sigma 1 and sigma 2 are same, but unknown. And that's why I'm using the formula on the page number 288. So please keep this thing in mind, guys. So sigma 1 and sigma 2 unknown. Let me write it down for you. So here let me change the color. Probably it is helpful since sigma 1 is equal to sigma 2 given, right? And unknown implies formula on page number 288. First formula. first formula, page number 28, formula, or you can say first formula, page number 288, right? And that is given in the form like what? X1 bar minus X2 bar minus T alpha by 2 and SP and 1 over N1 plus 1 over N2 is less than nu1 minus nu2 is less than X1 bar minus X2 bar minus not but T plus T alpha by 2 and SP and square root of 1 over N1 plus 1 over N2. If you plug the values, you're going to get that is equal to 0.565 minus 0.399 minus T alpha by 2, as I told you. No, I did not, right? How much confidence of interval? The confidence of interval that is equal to 95%. Let me calculate that one here separately. So if I calculate this one separately, 95% of the confidence interval is 0.095, and therefore I'm going to get 1 minus 0.95. So 1 minus 0.95, that is equal to 0.05, and that is my alpha. So alpha by 2, that is equal to 0.025, and therefore 1 minus 0.025, that is equal to 0.975, and this 0.975 in my degree of freedom V is equal to N1 plus N2 minus 2. N1 is equal to 10 plus 10, that is 20 minus 2, that is equal to 20, right? And 10 plus 2, that is equal to, so it is 18, my bad. So it is 18. So if you look at this number, 0.975 in your table A4, so here you have degree of freedom V, and here you have alpha values. So degree of freedom, here it is 18. Look at this line, and here you're going to get somewhere over here 0.975. Correspondingly, you can find your alpha value here, and that will provide you the probability. That means I can write T alpha by 2, that is equal to T 0.025, and here it is nothing but 2.101. So 2.1, that is from this one, no, sorry, yeah, here, and 2.1 and 0.1, 2.1 and 0.1 for degree of freedom, that is equal to 8. Okay, 18. So once you have this one, then after just plug the values. So let me just go back again to my example. And here I have negative of 2.101 and square root of 1 over 1 plus 1, also 1 over 10 plus 1 over 10, 1 over 10. And that is less than nu1 minus nu2, and that is less than exactly same value, right guys? 0.565 minus 0.399. I could have written down here plus or minus. Okay, that's fine. Plus 2.101 and square root of 1 over 10 plus 1 over 10. And I'm going to get that is equal to some value 0.033 is less than nu1 minus nu2 is less than 0.299. So that is your 95% of the confidence interval, 95% of the confidence interval. So that's how you can solve the examples, guys. I think I solve all kind of examples, number of examples we have solved over here. So that is more than enough. So let me stop over here, and we're going to start a new chapter next time, because paired observation and all other things, I think that is okay. But we are not going to cover that thing over here. Single sample estimation, no, that we are not going to cover over here, but we are going to start a new chapter next time. Thank you, guys. Thank you so much for your patience. And now let's stop, clear the picture, stop sharing this one, and let me stop my recording too. Thanks again, guys. See you next time. Have a nice time.